Hello, in this video we will continue talking about the van der Waals equation and how we can derive different expressions from the van der Waals equation that will help us in many different chemical engineering applications. Now, before we jump into that, what I would like to do here is just go through this document here that I have in front of me. Now, essentially, what is on this document? It is talking about the various improvements that have been made to the van der Waals equation over time. Now, the original van der Waals equation is very famous because of the thought process behind the equation. Van der Waals was really the first person to think about this B excluded volume here and the interactions between the molecules for a gas in a non-ideal state. However, over time, there have been some improvements made to the van der Waals equation in order to improve the accuracy of the equation. And what we're going to be taking a look at here is what is known as the generic cubic equation of state. Now, this equation of state makes two different changes. So the first change here is this A parameter here that you see is now dependent on the temperature. And we also have two new parameters here, this epsilon and sigma. Now, you might ask, well, what is epsilon and sigma? Well, if we scroll down here to the rest of this document, you'll see down here we have different equations of state. So the van der Waals, RK, SRK, different equation of state equations. And here we have the sigma and epsilon that would be plugged in to these equations in order to do calculations. So that is the two new parameters that have been added. Now, what also is different about this cubic equation of state is this the A and B parameters they now have new expressions. So if we scroll down here, these have been updated and improved too, and they go as follows. So the B parameter equals this expression, and the A parameter, again, that's dependent on the temperature, is equal to this expression here. Now you might notice that there are some different new parameters here in these expressions. So you see here, and there's a couple down here. Well, we don't have to worry about that because in this document and using the generic cubic equation of state, when you're doing any equations or calculations or anything like that, these are already pre-recorded here in this table down here. So if we were looking at the van der Waals equation, here are the extra parameters for the A and B parameter expressions up here. So again, this is just plugging these in, and this allows the van der Waals equation to be more accurate, and this accurate version is known as the generic cubic equation of state. Now, what we're going to be doing next in this video is we're going to be looking at a situation in where we know the pressure and temperature of a substance, but we want to know the V, the specific volume of that substance. So in order to do that, what we need to do is we need to set up the van der Waals equation and set that equal in terms of the compressibility factor Z. Now, if you remember, Z, the compressibility factor, is equal to PV over RT for an ideal gas. So using that information, what I'm going to do here is I'm going to derive this equation in terms of the compressibility factor, which would help us ultimately solve for the specific volume of a substance if we knew the pressure and temperature. So I'm going to switch gears here, and we're going to go ahead and derive for the in terms of the compressibility factor. Okay, so we'll go ahead and start with the general cubic equation of state, which again is P equals RT over V minus B minus A, and the A parameter here again depends on temperature. This will be over V plus epsilon B times V plus sigma B. Okay? Now what we'll want to do here, since we want to express this equation in terms of the compressibility factor Z, we remember that Z equals PV, or excuse me, this is PV over RT what we can see here is that if we multiply this equation by v and divide it by RT, we can set this in terms of z. So we can actually set this equal to z here. And if we multiply each term by v and divide by RT, that will give us v, and dividing by RT will have v minus b minus a times b. And going forward here, I'm not going to write the parentheses t next to the a parameter, but it is important to remember that the a parameter does depend on temperature. So here dividing by RT, we'll have RT times V plus epsilon B times V plus sigma B. Okay? Now the next step here, we're going to divide both the numerator and the denominator by V, the specific volume. So doing that, we'll have Z equals 1. Both the numerator and the denominator dividing by V here. So we'll have 1 minus B over V. Okay, and then that will leave us with A over V RT times 1 plus epsilon B over V, again dividing by V, but since we only have one V term here to divide by in the denominator, that will leave us with V plus sigma B. Now, we will want to get these terms all in like terms, so what we can do here is we're going to divide this last term on the right here by V as well. So that will give us Z equals 1 over 1 minus B over V minus A over VRT times 1 plus epsilon B over V. Okay, and then dividing by V here, we'll have 1 plus sigma B over V. Now, if we remember here, since the compressibility factor equals pressure volume over RT, what we're going to do here is we're going to solve this for the specific volume V. So what we get here is that V equals RTZ over P. Now what I'm going to do here in this next step is I'm going to plug in this expression for V into each of our V terms here in this equation. So I'll go ahead and erase this, and we're going to go ahead and plug in this Z expression. Okay, so go ahead and rewrite this equation here. So we have the compressibility factor equals 1 over 1 minus B over V minus A over VRT times 1 plus epsilon B over V times 1 plus sigma B over V. And again, we'll plug in our expression for specific volume. So we have RTZ over P. And if we go ahead and plug that in, we will be left with Z equals, let's see here, have 1 over 1 minus BP. Flipping that, we will have over RTZ. So just flipping that fraction in the denominator there. And we'll have minus A. And actually what we can do here, this first term here, we can look at these two terms here, this A over VRT. So this will have A over RTZ times RT, and this will be divided by P. So what we can do here is simplify this, and we will end up with AP over R squared T squared times Z. Okay, so we can go ahead and put this on the top of this fraction. So we will have AP over R squared T squared times Z, and this will all be over 1 plus epsilon BP, and flipping, so we have RTZ and this will be 1 plus sigma BP over RTZ. Okay, so now what we're going to do here, we're going to introduce two new parameters that have expressions that will help us simplify the equation where we have it right now. So the two new parameters, the first one is what is called beta here, and beta is equal to BP over RT. Okay, now the second one that we're going to introduce here is Q, and Q equals A over BRT. Okay, now what we're going to do here first is substitute this beta term in here. We notice that we have three of these terms here that we can substitute in for. So if we substitute beta in here, we will have Z equals 1 over 1 minus beta over Z. Okay, so BP over RT will give us beta over Z, and we will subtract here. I'm going to write this as A times P over RT times 1 over RTZ, which will make sense in a second. And this will all be divided by 1 plus epsilon beta over Z, again, BP over RT substituting in beta, and this will be multiplied by 1 plus sigma beta over Z. Okay? Now, what we can do here is we can actually look at this top term of this fraction here. So let's go ahead and write, we'll have the compressibility factor Z equals 1 over 1 minus beta over Z minus, and this we can actually simplify will be A times beta over BRT. So what we notice that is this chunk here, this is actually equal to Q. And excuse me, this will be multiplied by 1 over Z as well. So this chunk here will be equal to Q. So we can go ahead and rewrite this top 2. So go ahead and insert that. So adding that in, that will give us Z. Again, keeping the same here, we'll have 1 over 1 minus beta over Z minus Q times beta over Z. Remember, because we still had that 1 over Z, so we have to bring that into the denominator here. And this will all be over, again, 1 plus epsilon beta over Z times 1 plus sigma beta over Z. Okay, so we are down to this expression here. Now, what I'm going to do next is I'm going to actually move this Z here into the denominator, but I'll go ahead and erase and rewrite what we're left with here. Okay, so again, what we have here, again, moving that Z to the bottom, we'll have Z equals 1 over 1 minus beta over Z minus Q times beta. Again, moving the Z to the bottom, we'll have Z times 1 plus epsilon beta over Z times 1 plus sigma beta over Z. Now, what we're going to do here, this next step, is we want to divide each of these terms by Z. This will allow us to really simplify this equation. It clears out a lot of terms. So if we say Z over Z, and dividing everything by Z, I have 1 over Z times 1 minus beta over Z, okay? And then dividing this by Z as well, we'll have Q times beta over Z times 1 plus epsilon beta over Z times 1 plus sigma beta over Z. And this here, again, we'll divide by Z. Okay, so multiply Z there. Now, what we can do here is we can actually just start not canceling out terms, but I don't know what the right term is, but um, multiplying our terms through, I guess. And this will allow us to simplify this expression down the whole lot. So we'll have 1 equals 1 over, again, multiplying throughout, we'll have z minus beta. And then we'll have here, we'll have q times beta times z plus epsilon beta. And multiplying through here, and then multiplying through here, we'll have z plus sigma beta. So you see, this really cleans up the expression a whole lot. Now, I'm going to erase this because we're going to need a lot of room for the next part. Well, actually, I can start right here. So what we'll want to do here is we'll want to express this as a cubic polynomial. Now, in order to do that, what we're going to need to do is find a common base here. So if we do that, we can see here we'll have z minus beta, and this will be times z squared plus epsilon plus sigma, okay, and this will be times beta times z, make that a little bigger, and this will be plus epsilon sigma times beta squared. Okay, so this will give us our common denominator, and then subtracting the q times beta term, we will ultimately be left with again the same here. So z minus beta times, or actually we don't need the z minus beta here. That will go to the q times beta term. So here we will have z squared plus epsilon plus sigma times beta times z, and then plus epsilon times sigma times beta squared, okay? And again, we will subtract the q times beta term, so we will have q times beta times z minus beta, okay? So I'll go ahead and erase all this, but what I'm going to do is I'm going to rewrite this at the top, and we will need to see what our coefficients are for each of the terms in our cubic polynomial. So I'll draw it out in a systematic way so we can see each of the coefficients that we'll need to add and subtract in order to get our polynomial, but I'll go ahead and erase this so we can see it all drawn out. Okay. So again, here our equation is we'll have z squared, and then we'll have plus epsilon plus sigma times beta times z, and this will we will add epsilon times sigma times beta squared here, and then we will subtract the q times beta term, have that multiplied by z minus b. So now we will be able to set up a systematic approach in order to determine each of the coefficients for each of our values. So we will have a z cubed value here. We will have a z squared value. We will have a z value, and we'll have a constant. Again, these we will draw out the coefficients for our cubic polynomial that we are solving for. So I'll go ahead, and for the sake of time, I'm going to head and skip through this and write through all of the coefficients. I'll go through and explain how I do that method, but in order for the sake of time, I'm just going to go ahead and write them out for us. Okay, so I've gone ahead and rewritten our second expression up here on the top, and what we would need to do with this expression is actually subtract from here over to the left side so that we can evaluate these coefficients as well. But again, essentially we have a z cubed term, a z squared term, a z, and all of our constants here. Now, what I've done is I've gone ahead and shown all of our coefficients for each term. And just to give you an example of how this method works, let's take a look at, for example, this z times this last term here. So if we have z times epsilon times sigma times b squared, that will be a coefficient in terms of z. So the coefficient in terms of z will be this epsilon times sigma times b squared. Okay? Now, what we would need to do if we wanted to write this as an entire cubic polynomial simplified out, we would need to add up our coefficients and write out the entire cubic polynomial. Now, I won't do that just for the sake of time and space on the whiteboard, but I think you get the gist of how we would add up these and then express that in a cubic polynomial. Now, if you remember, so what is the importance of why we want to express the general cubic equation of state in terms of the compressibility factor? Well, let's say, and I talked about this in the previous video in this video series, but let's say we have a problem where we're asked to solve for the specific volume when we know the pressure and temperature, but obviously we don't know the specific volume. We would need to express the general cubic equation of state in terms of the compressibility factor first in order to solve for the specific volume. Now actually, and this is what I'll be doing in a later video in this video series with the equations of states, I will be taking the roots of this cubic equation, and that will allow us to solve for the specific volume if we're given that type of problem. But that's it for this video. That's how you express the general cubic equation of state in terms of a cubic polynomial. That would be in terms of the compressibility factor. So that's it. Thank you for watching.